screw conveyors and muck removal systems in this table. Again, this picture shows how ribbon screws work in removing the boulders. As you see, this little blob here is supposed to be a boulder that's ingested by the screw, and the space between the screw blades is such that allows this boulder to be ingested, and then by action of the screw, this boulder is transferred to a point at the close to a discharge point. If the size of the boulder is smaller than roughly 1/3 of the diameter of the screw, then this can pass on and go through the discharge point and go to the remaining or the rest of the muck handling system, whether it's a conveyor or a muck car or whatever it is. But if it's larger than that 1/3 of the diameter of the screw, then a gate close to the discharge point has to be opened up, and the large boulder can be removed from the gate. This is a picture of the ribbon screw. As you see, there's no shaft, and that allows for fairly wide space between the blades of the screw. And just like the shaft screw, it can handle the pressure difference, pressure in and pressure out, as well as handling boulders. And this is a picture of a typical gate that's installed on these screws. It's just, we put this picture in this presentation to just give an indication or a feel to the audience as to the size of the structure that we're talking about here. Now, the next important aspect of EPBs is how they negotiate curves, these machines. There's a video here that I will start very soon, and that basically explains the principle of active articulation versus passive articulation.
Using a process called active articulation, Robin's EPBs can produce tight curves with a radius as small as 3 to 4 times the tunnel diameter. Active articulation allows the thrust to be transferred equally to the entire circumference of the segment ring, eliminating the problem of ring deformation. The articulation occurs between the front section and rear section, which are connected by articulation cylinders. Other EPBs use a process called passive articulation, which places uneven pressure on the rings while steering and causes deformation of segment rings.
Okay, the video is finished, so we move on with the presentation. A little bit short of time here. This slide actually shows active and passive articulation side by side. As you see, in active articulation, the forces of the thrust cylinders are applied uniformly to the segments, and they are perpendicular to the segments, whereas in case of passive articulation, the forces are uneven, and they are applied at an angle, so there is the potential for displacing and moving the segment depending on the direction of the steering of the machine. One important point to mention here is this skid effect that we have shown on this slide. It is important to understand that in very soft soil where the ground cannot create enough resistance in front of the machine to allow the machine to steer properly, even if we articulate the front of the shield, the machine will have a tendency to continue to go straight. We need to have the ground resistance to allow this steering action to commence and the machine to go into that steering mode. If the ground is too soft, then additives have to be injected to change the properties of ground and create that resistance that the machine needs to negotiate the curve. As you see, the active articulation, the forces are even. In case of passive articulation, the forces are uneven. Now, this is the single most important aspect of EPB operation, reducing and controlling the surface settlements. And this could be achieved by efficient backfilling systems that we install on TBMs. By immediately routing the annulus between the outside of the segment and inside of the board tunnel, and immediately behind the tail shield, we have reduced the possibility of ground settlement. To decide on the backfilling system, there are some factors that need to be considered. Obviously, the risk of settlements and the location of the tunnel in densely populated urban areas. Obviously, we cannot afford to have any settlements in the not so densely populated areas. Then settlement may not be a problem. Stability of the segmental lining is a factor to be considered. Water tightness of the segmental lining, and of course, the geology of the tunnel. And the decisions that the contractors and the people who decide on the configuration of the machine have to make are whether they want to inject grouts through the segment or through the tail shield, or what type of grouts they want to use. One component grouts, or one liquid grout, or two components / two liquid grouts. Ground deformation can be divided into three different zones. The first zone is in front of the machine. The second zone is immediately behind the machine. And the third zone is far behind the machine. And the future slides actually will go into detailed description of these areas. In front of the machine. As we said, EPBs are good for controlling the face pressure. And we always have pressure in front to stabilize the face. And any muck removal from the face has to have this important item in mind. The face has to be supported at all times. Now, if we do not remove enough material from the face and allow the pressure on the face to increase, we will have a phenomenon that's called heaving. The surface, this line is an indication of the surface. The surface may heave up like this. Conversely, if we remove too much material from the front, the pressure drops and the surface settles, as shown here. So, face pressure control is a very important factor in design of any EPB machine. Now we move to tailboard, which is far behind the machine. As the machine advances, obviously, there is a difference between the inside diameter of the tunnel and the outside diameter of the segment that's shown by this yellow zone here, which is a void. If the void is not filled quickly and properly, what's going to happen is that the ground will come in and fill that void. See that all that yellow zone has been turned brown, which is an indication of ground moving in. And when the ground moves in to fill that void, what happens? The surface actually settles. And this happens far behind the machine. By properly injecting grouts in this clearance between the segment and the tunnel, we will prevent that further ground settlement far behind the machine. Now, these are two different kinds of applying grouts to the clearance area outside of the segment. The left side is grouting through the shield. The effect is immediate as the machine advances, as the segments are installed. the grout is injected through the shield into that cavity here, and there is no possibility for creation of voids that will result in any ground settlements. Some projects, some people to reduce the cost or to reduce complication of the machine design, they decide to grout through the segments. But the disadvantage here is that grouting through the segments has the potential to create a void. Excuse me, a void just behind the tail shield and in front of the segments, which is shown in here. And this void is very detrimental to the settlement, to the surface. It will create ground settlements. Maybe just highlighted that void. The differences between the type of grout that is used. One liquid or one component grout, two liquid or two component grouts. The one component grout has higher viscosity, so the flow rate is very poor. The two component grouts have excellent flow characteristics because it's less viscous. There are more injection ports are required for one liquid grout, and fewer injection ports are required for two liquid grouts. And most importantly, when we are using one component grout, the loading on the segment and the pressure around on the segment is uneven, whereas in two component grouts, the loading is low and the pressure is distributed more evenly around the segment. And you will see this in the next slide. In very stiff grounds, there is very little difference between one component and two component grout application. Again, yellow means clearance that has to be filled by grouts, and which is one component grout on the left, and two component grouts on the right. And practically there is no difference between these two grouts. So one component being less expensive was probably more desirable in this case. But in case of soft ground, there is a difference. The one component grout, because of low fluidity and high viscosity, it has a tendency to create pockets of concentrated grout, pockets of high pressure, and uneven distribution around the segment. Whereas the two liquid grouts flows more evenly and covers that gap more evenly. These two curves show the curing characteristics of two liquid and one liquid type. As you see on the red curve, as soon as liquid A and liquid B, which is the accelerator, are mixed, the curing starts very shortly after mixing of the two liquids. And this short period of time is desirable because it allows for spreading of material evenly in the gap. And then about half an hour, 45 minutes after mixing, the curing period starts, and the mixture gains strength as the time goes on. In case of one liquid grout, the curing doesn't even start until about 4 hours after application. And then it will have a high rate of gaining strength during the time initially, but eventually it kind of gradually evens out, and a few tens of hours after application, they will probably have the same strength. This is a picture of the state-of-the-art grout through shield equipment, which we install on the tail shields. And this is a schematic of how it works. Grout, the liquid A is injected through this pipe. Liquid B is injected through this pipe, and they mix just before the point of application. And when the machine is stopped to prevent liquid A from setting in this pipe, high water pressure could be actually supplied to this pipe